Hi everyone, welcome to my channel. This time around we are looking at work done in elastic materials. This video is a continuation of the video of elasticity and Hooke's law. Okay, now provided that the deformation is within elastic limits, as we discussed in Hooke's law, the work done in stretching or compressing an elastic material is equal to the elastic potential energy stored in the material, and it is given by these two equations that we can see here. Okay, that is work done in stretching or compressing elastic material, or the elastic potential energy stored in an elastic material is equal to half Fe or half Ke square, or you can as well say is this work done equal to half F square over K. Okay, where our F equal to the force that is causing deformation, or the restoring force in the material. Our K is the force constant. IE is the deformation, that is extension or the compression in the elastic material. Okay, let's quickly look at some examples here. Example 1 says a string is stretched 40 millimeter by a force of 15 Newton. We have to calculate the work done by the force. Okay, now doing this, we brought out all the parameters in this question. That is the extension equal to 40 millimeter, converted that to meter, we have 0.04 meter. We have force that is causing the extension as 15 Newton. So to find the work done with the parameter given here, we can find our work done using half Fe. That is the first equation that we were given here. Okay, substituted all the parameters into this equation. We have 1 over 2 multiplied by 0.04 multiplied by 15, which is equal to 0.3 joule, as we can see here. And okay, let's check another example. In our second example, we have a spiral spring which is compressed by 0.2 meter. We have to calculate the energy stored in the spring. So from the equation, we have E to be equal to 0.02, that is the compression. And we have the force constant given as 400 Newton per meter. We are looking for elastic potential energy. Okay, using this equation, half Ke square, and substituting the parameters into the equation, we have half multiplied by 400 multiplied by 0.02 square, and that will give us 0.08 joule as the answer. Okay, let's consider the third example. In our third example, we have a stone of mass 20 gram which is stretched, or which is released rather, from a catapult whose rubber has been stretched through 4 centimeter. If the force constant of the rubber is 200 Newton per meter, we have to calculate the velocity with which the stone lifts the catapult. Okay, from this question, we have a given parameter mass of the stone as 20 gram, which is equal to 0.02 kilogram. That is, we divided it by 1000. We have our extension to be 4 centimeter, which is equal to 0.04 meter. That is, we divided it by 400. We have our force constants to be 200 Newton per meter. Now note, in this question, the elastic potential energy that is in the rubber that you stretched is transformed into kinetic energy of the stone, because once you release the rubber, the stone will just speed off from the rubber, and that is why we equated half Ke square to half mv square here. That is half mv square, which is equal to the kinetic energy of the stone, while half Ke square equal to elastic potential energy of the rubber of the catapult. Okay, now using that relationship, because here we are just experiencing something that we call energy transformation, so substituting all our values from the equation into the two equations, we have half multiplied by 200 multiplied by 0.04 square on this part, which is equal to half multiplied by 0.02 multiplied by v square. Making v the subject of the formula, we can take out this and this, and multiplying this, dividing it by 0.02 will give us 16. That is v square will be equal to 200 multiplied by 0.04 square divided by 0.02. Remember, we've taken these two parts away. They cancel each other out. Now, if you press this on your calculator, you're going to arrive at 16. And finding the square root of both sides, V will be equal to root of 16. And that is 4 meter per seconds. And with that, we come to the end of this particular equation, or this particular topic worked on in elastic material. If you have any question, feel free to drop your question in the comment section, and the question will be attended to. Thanks for watching.